Okay, so let's start with the third lecture. Before that, two quick things. The first one is that yesterday afternoon, I realized that some of you were there was some confusion with exercise number 3, the one about the correlation function. So what I did is I solved it, and if those of you that were having troubles and still have unclear things, you can find me this afternoon and we can discuss it together. I can also give you the solution. It's not A to B, but it's solved, and then you have to do some algebra. But if you have any doubt with that, we can discuss it so you don't invest as much time on it, because again, I want to reinforce that it is not as important as the ones that come after it, okay? But it's still interesting. I mean, I still very happy that you are interested on it. So now we have the solution and we can go step by step, because there are some subtleties in this when you solve it that are not explicit in the problem, and that's why you are having some issues with it. The second one I wanted to say is I said yesterday something in the class that I think created a lot of confusion, and it was when I was deriving the master equation, and I was telling you that when I am in a state n and I want to calculate the probability that nothing happens, I told you that I think I said I have to sum. What I have to do is I have to add the two processes that would leave me out from that state n, which was, we said, the probability that non-particle goes from 1 to 2, and we wrote this, and then the probability that no particle goes from 2 to 1, and I wrote this, if I remember right. Was this? No, because this is no, sorry, without this, and the power. So I have to add the contribution of these two processes, which means that I have to multiply these probabilities, because I need the probability that none of them happens, and the same way that when we want the probability, this would be the probability that one particle does nothing, and I have n particles, so I multiply n times. I have two processes, so I multiply both probabilities. I don't sum. Because many of you ask me, like, what happened with the two? What happened with the two? At some point, someone asked in loud voice, and I was very lost and confused, and I create a confusion. So what happens is that you multiply these two things, and then because you are at first order in DT, you get the term that I wrote, okay? Good. Great, so that being said, let's go to what we're going to do today. What we're going to do today is to get a little bit deeper into the example that we were working yesterday with, and then we are going to transition to a one that is slightly more complex and also a little bit closer to biological motivations, because my goal is assuming that none of you here likes, I think it's fair to say that no one here came because the course in biology. And it's fine. That's something I learned how to live with. My goal is that at least at the end of the course, let's say 2 of you take some book in applications of physics to biology. Then I will be very, very, very happy. I'm not going to be as ambitious as other years in which I was hoping that one of you would do the masters with me. Let's keep a little bit humble so I don't get disappointed. Great. Yesterday we had this master equation. We learned how to solve it with generating functions. And even we realized that we don't need the master equation to obtain this probability, because it was a very simple process for which we could obtain the binomial distribution as the solution for this problem. Some of you ask me, but if I have interactions between my particles, then it's the same. It's still a binomial. It's just P1 and P2 that is changing. You need to be careful with those lines of thought, because an important thing between a binomial distribution is that I need a sequence of independent Bernoulli trials behind it, for those of you that are familiar with that. So you always need to keep independence between your trials. And if you lose it, then the picture changes. So what I would like to ask you now to do is to go back to yesterday, before you knew that generating function existed, and let's think that we are not able to solve this equation. We are not able to solve the master equation, and instead of trying to obtain the full probability distribution function P in T that would give us all the information about my stochastic process, I'm going to say, well, I cannot get this object here, but instead, I'm going to try to characterize the moments of this distribution. Of course, one way of obtaining the moments of the distribution is if you, for example, have the distribution already, then you can compute the first moment. Like this. You can compute the second moment like this. This is just the definitions of the moments for a discrete probability distribution function, for a probability distribution function of a discrete random variable. And in general, you will define the k moment, or the kth moment, as the sum infinity n k p n t. So of course, if I know the probability distribution function, then I can compute this and I have the first moment. The thing is that we don't know the probability distribution function. Yes.
So you're writing the master equation for ICTP process, right?
I'm writing the master equation we had yesterday. That is going to be our departure point. Remember that this was a system in which I had two states and I had omega 1, 2 and omega 2, 1. This is the process I have in mind now.
So if the question were like explicative instead of additive, it would still hold, or?
So the definition of the moment is the same, because all I'm doing is I am defining the moment of the distribution, which is, in this case, is the mean value. So you multiply n times the distribution and you sum over all n's. If this is a random, if this was a continuous variable, maybe you're more familiar with this in terms of integrals, but it is just the discrete version of it. If I have a different stochastic process, what is going to change is the master equation, and that's what we are going to do in 20 minutes, more or less. Great, so if I have the probability distribution function, I can compute the first moment, let's say. Let's start with the first moment, but of course I don't know the probability distribution function. So what I'm going to try to do is to write an equation for it. So I have my master equation, I cannot solve it, but the same way yesterday I wrote an equation for the generating function, I can try to write an equation for the first moment of this probability distribution function. So the way I can do that is saying, well, I'm going to take my master equation, and the same way I did yesterday, I'm going to multiply it all by this summatory. And, okay, let's write it. Omega to 1 n minus n plus 1 p n minus 1 t plus n plus 1 omega 1 2 p n plus 1 t minus omega 2 1 n minus n plus omega 1 2 n p n t. So I multiply my whole master equation by the by the sum of by n, and I multiply it by n and I sum over all n's. Very similarly to what we did yesterday, the left sign I can switch the order of the sum and the derivative, so this is already straightforward. And now I have a series of terms that I will need to manipulate with care. I'm going to do that explicitly for this case, and like always, the next cases are going to be in the exercises, and it's for you to do as homework. It's important that at least you do this once in your life right, which means that probably you need to do it 15 times until you get mechanical with that. So here I have these two terms that if I open them up, they are already very user-friendly in the sense that I have n, capital N times N, P, and T. And this is multiplied by N, and I am summing from N equal to 0 to infinity. Yes. Sorry again? Why are we calculating the moments of the distribution? That is a very important question. So here the question is, why are we calculating the moments of the distribution? The reason why we are calculating that is because I am asking you to do the effort of thinking that you cannot solve this. You can tell me, well, your question is why I calculate the moments if I can calculate the full distribution, or? Okay, perfect. So what is the use of the moments of a distribution? That's a very important question. The moments of the distribution are going to give me information about the structure of that distribution, but only partial information about the structure of this distribution. So for example, imagine that your distribution of the number of particles would be not a binomial, would be a normal distribution, something like this. This is n here, and this would be, okay, P of n. Okay? This would be the solution of this master equation. The moments of the distribution are going to give me information about the structure of this distribution partially. For example, the first moment of the distribution is the mean, right? This is the definition of the mean value of a distribution. So in the case of the normal distribution, it's going to give me this value. Instead of telling me what is the probability that I have n particles at time t for every n, which is the information that I have here, it's going to tell me on average how many particles do I have. So, okay, I don't know I don't know what is the probability that I have 5, 6, 7, 8, 9, but I know that on average, if I measure my experiment many, many times, I will have 10. The second moment is related to the dispersion of this distribution. So it is going to tell me, okay, if my mean is 10, my first moment is 10, and my second moment is very big, then my distribution is going to be very open. But if my second moment is very small, then my distribution is going to be very, very narrow. So it gives me an idea of how much my number of particles are going to be dispersed around the mean value. So it's a way of saying, okay, the full distribution, I cannot get it. I'm going to try to get partial information. So for example, if I give you the first and the second moment, I don't know if my distribution is a binomial, but I know that on average I will have 10,000 particles and that the fluctuations are not going to be very relevant around it. Okay? Higher moments contain higher information about the distribution. Something that is really good is that, for example, for the normal distribution, if you know the first two moments, you can write any other higher moment in terms of the first and the second. But maybe that's for the future version of yourself in a couple of years when get more in detail into this. For now, what is important for me is that you understand that these moments of the distribution, they contain information about the distribution, partial information about it, okay? So maybe we can write here with words. So this is clear that what we are looking for is, in this case, the mean. And let's put here something like proxy for fluctuations, dispersal or dispersion around the mean. Okay? So these are the two ingredients that we are going to try to look for, yes. There are some cases in which, well, for example, if you have a normal distribution and you have the first two moments, then you know you can reconstruct the distribution, and then other than normal distribution, if you can apply the central limit theorem, many distributions, which is related to when these approximations are accurate. So in principle, getting the first two moments, we are going to see it in a little bit in comparison with some simulations I prepared for you. If you get the two first moments, for most of the cases, if you have extreme statistics like power laws and things like that, then things are a little different. And always discrete distributions, okay? All right, so yeah, these questions are important. I prefer that you ask me these questions so you have the concepts clear than I spend time doing the algebra first, because the algebra you can do it, and second, because I will do it wrong anyway. So it's good that we get clear with concepts. Great, so what do I have here? I have two terms. The first one is capital N, and now I have small n omega to 1 p n t. So this is basically omega to 1 sum 0 to infinity, and now I have n times p n t, n times p n t. So what I have here is capital N, omega to 1, mean value of n, all the first moment of n. So this term is easy. If you do the same algebra, what you will get is in the second term, omega to 1, and the second moment, you have n times n, p n t, summing n squared. This other term here is also simple, because it's exactly like the other ones. So what we have is omega 1, 2, n squared p n t. So this is omega 1, 2, mean value of n squared. Okay? These are easy. These, we don't have any problem with that. Let me try to do now this one. So for this one, I have the sum from n equal to 0 to infinity, n times n plus 1, n times n plus 1, omega 1, 2, p n plus 1 of t. And here's where I start having problems, because my indexes are not matching. So I have to do manipulations to try to rewrite everything in terms of p and t, so I can apply my definition of the moments, which is what I am looking for. So this is very similar to a calculation we already did. So I'm going to call n plus 1, I'm going to relabel it by m, which means that n is equal to m minus 1. And now I just shift my indexes. When n is equal to 0, m is equal to minus 1. And now I have n plus 1, which is going to be m minus 1m. Omega 1, 2 is a constant. And pn t. So now I have, sorry, m. p mt. So now I have already pmt here, but yes? Okay, 1. N equal to 0. Yes, when n equals to 0 is 1. Great. Still, it's still a problem, right? Because I am missing one term.
Would it be easier to define the summation over minus infinity to plus infinity?
Here we have a question, because someone studied yesterday's notes. Wouldn't it be easier to define the sum from minus infinity to plus infinity? But then I have a problem, because n only goes from 0 to infinity, right?
But you can put the probabilities to be 0.
I can put them. Why can I mean, I cannot put them. I can put, or they are equal to 0, right? Yes. So in principle, I could have started as he's saying from minus infinity, because every probability with n smaller than 0 is 0. The way I did it here is just to make you think about that. And also because now actually I don't have too much of a problem, because the term with m equal to 0 is equal to what? 0. So I can put here 0. That's why I didn't think too much about where the index starts. Great, so, and then of course, M is an index. So I can call it M, I can call it N, I can call it whatever I want. So basically this is equal to omega 1, 2, of course, that goes out. And this is mean value of N squared minus, mean value of N squared minus mean value of N. No? Oh, yes, great. So you can do the same with this term here. Just manipulate the indexes a little bit to have some fun. And what you would get at the end of the day is this expression already for the mean value of N. So we would get well, before writing the equation, let me explain you why some things are going to simplify. So notice that here I have, where it is, this is omega 1, 2. This is omega 1, 2 here. So here I have omega 1, 2 times the mean value of N squared, right? That it was coming from this contribution here. And I have the same omega 1, 2 mean value of N squared that is with a different sign because one comes from the gain term and the other one from the loss terms. So some of these terms are going to cancel each other. That always has to happen, so it's a good check for your calculations. And after working out this term that I am skipping and rearranging things, this is what you would get. Yes. So you get a very, very simple ordinary differential equation for N, for the mean value of N, the mean number of particles in state 1. If you, for example, try to look at the stationary state solutions, so basically what is the mean number of particles that I will have in a state 1 if I wait infinitely large, or infinitely long, not large, then this value that I'm going to call mean value of N in the stationary state is going to be N times, capital N times 2, 1, divided by omega 2, 1 plus omega 1, 2. Yesterday, we found that the solution of this, the solution of this equation was a binomial distribution with total number of particles N and probability P1 that was omega 2, 1, omega 1, 2 plus omega 2, 1. You can check your notes. Oh, this should be one of the, in the stationary state, stationary state, T to infinity. So this is what you should have obtained yesterday in the problem number 4, I think, for one single particle. So what is the mean value of a binomial distribution? The mean NP. And then this is NP. So far, so good. So even in cases where we cannot obtain this probability distribution function, I can work out expressions for the mean value. You could try to do the same for N squared if you want, and you get information about it. Questions up to here? No questions? Well, I think it's fair that there is no questions. I think this is kind of a continuation of what we were doing yesterday. I saw many of you studying hard. So I'm going to assume that you will ask me later. Great, yes? That's why sometimes you need to work higher orders of the higher moments of the distribution. I mean, if you have, for example, a distribution that is bimodal, and the mean value is wherever it is, you still get it. Whether that's useful, you are right. So the question is, what happens when the mean value is not useful? Well, you need to go to higher moments. And there are also some cases we will see in a while in which this is something that is very important. What I've done for this problem is exact. So this is the exact solution for the mean number of particles that I will have in state 1. This is an exact result. What we are going to see now is that sometimes things are not as pretty. Yes, another question. How many of those moments you need to know in order to have enough information? So in all the situations I faced so far and all the material I've studied so far, again, I know I sound repetitive, but if you are working with systems that are large enough, in principle, you can, it is not that you only need 2 moments to characterize your process, but if you have 2 moments, you can characterize, you can write down all the other moments, basically. Sometimes it depends. So usually the best, what people usually do, you would do some numerics on your model. If we're talking about a realistic scenario, like real world problem, you would run some numerics, and then that gives you intuition on how probabilities look like and what is the, what you are looking for. You don't go blind, no? It is not that I give you now, okay, I have this problem. I have 4 species, X plus Y gets Z plus 3A gets 7B. Give me the distribution of B. You don't start, usually you don't start writing the master equation, and, well, at least I don't advise doing that. You get some numerics, you get an intuition on the structure of your process, and then you try to get information about the distribution that you're looking for. And this is very important because as power laws have appeared a couple of times already in your questions, there are some times in which you have distributions for which these moments are not even, they are not even defined, no? So you have to be careful with that. Great, so let's move to a problem that is slightly more tricky, but will change a lot our capabilities. All right, so now you're going to allow me to get a little bit nostalgic as we get closer to biology. Let's imagine that we have a population of animals. And this population is living on an island. This is a pretty island. It's called Tenerife. And in this island, I have my population, and I have this species that is following the birth-death process. Let me see which letters I use for the rates in the notes. Beta. So basically, these animals, they will reproduce at rate beta. They will die at rate delta. And now I want to account for a further process, because I'm going to say, well, these animals, they need food to be able to reproduce. And the more food I have, the less there will be for each, right? So if tomorrow Donna Jo, instead of making 3 cakes, makes 1 cake, then you all will be there running each other and competing for food. That is the word that we would use in ecology. The way you can model that is to say, well, because I want to account for some crowding effect, I'm going to assume that these animals can also kind of collide each other. There is encounters between these two animals within the island. Let's say at some position where the food is, both of them arrive at the same time. And the consequence of that interaction is going to be that one of them dies. Only one of you gets the cake and I die because of starvation. This is a very, very basic way in which I can model the growth of a population with a limiting resource, if you want to start learning some terms that are very common in ecological modeling. You can think also that this is, for example, the contact of the transmission of a disease, in the sense that if, well, the connection with disease transmission would be a little bit more subtle, but basically the idea is that now you have an stochastic process in which one of the rates happens conditional to encounters. And what happens when I have things that depend on encounters? There are interactions, and this is going to be density dependent, right? So these pairs, the more I have, the more pairs I can construct, if you have combinatorics fresh in your mind. I can still write the master equation for this. Of course I can. I'm going to label n as the number of particles, okay? Or the number of animals. It's the same for us so far. And now it's kind of easy because I already know how this master equation is going to look like. I know the structure. I only need to sum over all possible changes in n, my step operator, minus 1, omega n to n minus L, P, and T. We already did it once yesterday, so this is fine. But now I need to define my transition rates. What are my transition rates? If I have n particles, or n animals, here in Tenerife, I only have two possible outcomes. From n, I can only go to n plus 1, or I can only go to n minus 1, because I'm always working with one-step processes. I have one animal reproduces, one animal it dies, two animals encounter, one survives, the other dies. Yes? Yeah, that's a great question. Why reproduction doesn't count as the interaction between two animals? Because I want to keep things simple. Because I want to keep things, we have here a potential ecologist in the room, that's good. No, it's true. If I want to do this properly, I would need to define, well, I would say, what is this animal? First of all, it wouldn't be a particle, it would be a rabbit. And then I would need to say, well, rabbits actually, yeah, to reproduce, I need a male and a female. So I would maybe need to elaborate a little bit more on my model. Yeah, that's a great question. Surprisingly, most of the times, this assumption is behind at least the most basic population dynamics models. And we are going to keep it like that. Although, exercise number 7 or 8, I don't know. There is one problem in the sheet that asks you to work a predator-prey system, which is when I have a fox and a rabbit, for example, or when I have a zebra and a lion. And in that case, you would have two populations. And the interesting point is that instead of having this term here, you would have a rabbit plus a fox gives me, sadly, only one fox, or two fox. I don't remember how I defined it. So a fox eats a rabbit, and because it gets so much food, it reproduces. That's a way of formulating this model. Then it's interesting because you have to write the master equation for what? How would you define the state of a system like this with rabbits and foxes? Two variables, probability of having m rabbits and n foxes. And then you continue all the way. Joint probability. Then you can marginalize and you can do things, but you define the master equation at the level of the joint probability distribution function for both of them. But this is an excellent question. Okay, let's go back to the transition rates. So who wants to tell me what is the rate omega n to n plus 1? Someone? Beta? Beta dt, I got a bit dt. Someone else said something else? N? Something else? No? What are the dimensions of this object here? Beta dt, what is the dimensions of this? No dimensions. What is the dimensions of omega? 1 over t. So I don't need dt. Dt is for calculating probabilities, right? Beta times dt times n would be the probability that 1 out of n particles of foxes or wherever reproduces. Great, so I need now a second volunteer to give me the other rate from n to n minus 1. Let's already put here plus minus 1. Sorry? Sorry again, pardon, sorry? Delta n plus something else. Okay, here we have a smart volunteer. N by 2 times gamma. This? Raise your hand if you agree with this. I heard combinatorics. That was easy to translate. So let's think about because this is the key thing that we have now new. N times n minus 1 divided by 2 omega. Who disagrees with this? Disagrees. I always found it harder when I say disagree because then you have to say why, and then people don't. So who else wants to explain me why this is correct? If you agree with this, then you need to agree for a reason. I'm counting the number of pairs that I can make with n organisms, basically. Yes? Yeah, n taking pairs. I need to count the number of pairs that I can make out of n particles, assuming and not counting the pairs twice. Can you compute that quickly for me? In your paper if you want, you don't need to tell me. Yes, that's correct. Yes, and if you simplify that? Great. Perfect. No, but I like that you need to do the calculation to convince yourself. That's great. That's perfect. Yeah, exactly. This is the number of pairs I can make with n particles, n factorial divided by n minus 2 factorial divided by 2 factorial. There is a small detail here that we are missing. And it's really, really important for modeling these systems properly. The way we are now defining this rate here we are thinking that we have particles, we have animals, let's say in a volume, is our island, and they need to encounter each other, right? So in principle, if I have the same number of particles in a smaller volume, these encounters need to happen more often, right? Do you agree with me? So this encounter rate, if you want, is actually volume dependent. So let's call it, let me use the same letter because L square. So I'm assuming that this is 2D and L square is the size of my system. If you look at the books I share with you to study this topic, or if you read many, many papers about this, the way this L square is introduced is always a little bit phenomenological. You say, well, this is density dependent, I need it to make things work. What is behind this L square is what? Can someone tell me, have an intuition of what is behind this L square? Sorry? It's to make it density. At the end, what you can think, once I write it like this, it's very easy to say, well, here I have n particles, and all I'm saying is that they encounter each other proportional to some density around them rho instead of number of particles, right? Makes sense. If the density goes up, then this guy is gonna die more frequent because of collisions. If the density goes down, it's gonna be more rare. But what is the physical model I have when I put L square here? How many of you have studied, well, chemistry, I think many of you know. So the way we are modeling here encounters is using the law of mass action. So what I'm saying is that the rate at which reactions happen is proportional to the product of the concentrations of these chemicals. In this case, it's a chemical with itself. And this is behind 100 years of research in ecological modeling. How many of you know the SIR model for epidemiology, where you have susceptible, infected? Well, if you read something about COVID in the last 4 years, it's all over the place. All these equations usually have a term that says that the number of infected people changes proportional to the number of infected times susceptible. It's the same. It's the same rationale that we have here. You may have a lot of questions that are, well, what happens when I assume that my particles are spatially distributed? What happens when, well, this is a very active area of research. That's, for example, one of the things we do in the group. What happens with these models when the law of mass action is not accurate and we try to model things the way they really move? Well, that's an active line of research. Anyway, let's go back to our master equation before I start. Losing track of what I should say. So I have the master equation, and we said that our goal was to try to understand a little bit the structure of this probability distribution. Yes? To keep the? This is a great question. Should we keep another constant to keep the units the same? I cheat a little bit here because omega doesn't have the same units as beta and delta. Omega over L, so actually let me correct this because this is going to be recorded. Usually that's the way you write it. But if I put there a system size, then it's like, why a system size now if this has no space? Blah, blah, blah. Yes, great question, excellent. Thank you very much. Okay. Now, question for you. If this is my master equation, let me remove the yellow square. If I look at our pretty master equation, look how condensed we can write it. What is the main difference you find between this master equation and the master equation we wrote yesterday? First of all, how many of you see a fundamental, well, fundamental here is a very risky word in this place. What is a big difference you see between this master equation? How many of you see a big difference between this master equation and the ones we had so far? No, raise your hand, sorry. Raise your hand if you see it, a difference. Okay, now shout whatever is the difference. N squared. This is a very important difference. My transitions rate now are nonlinear. And this is what is going to change. Well, everything sounds very, but it's going to change how much we can get from this equation, because now this is a nonlinear equation. But still, okay, we cannot solve it, but we can get the moments, right? I told you that when you cannot solve it, you can get the moments. So let's try to do it. I'm going to write the equation for time derivative of the mean number of particles. All right, so okay, let's do a couple of terms, and then you can finish it up. So this is equal to the sum from n equal to infinity, 0, and then I need to basically open up this. So this is a nice way of writing things up, but so far with the tools we have, we need to open it up. So let me open it up for you. So this is delta n plus 1 plus gamma n plus 1 times n divided by L squared. Let me do something else that it's going to save us a lot of time. I'm going to absorb the 2 into the gamma. So it's, at the end, it's the same. We don't have any quantitative number for anything. Then P n plus 1t plus, these are all the terms that you will need to calculate. Minus delta plus beta times n plus gamma L squared n minus 1 P n t. Okay. You now need to still work a little bit with the indexes the same way we did. It's all very mechanic, so I'm not going to do that. Sorry, I think I showed too much. And if you manipulate all the math, what you are going to get is this equation. Beta minus delta plus gamma L, mean value of n, minus gamma L squared, mean value of n squared. This is what you should get if you expand all the terms, shift the indexes, and do the same I did before. Yes. I can do one more. Simplification here. That in principle you don't need to do it. You can carry on your calculations with this as it is. But usually, if L is going to be very large, and then you can cancel this term here. Can I cancel this term here? This term goes with n squared, and this goes with n, so be careful with that. Because this is much smaller than this, but this can grow as much as n squared grows. Okay, so now I can solve this equation. No? Who wants to give me the solution for this equation in the stationary state? Anyone? Anyone thinks that this solution cannot be solved? Because this is, come on, it's a very simple equation and you are thinking there for 3 hours in the stationary state. This equation has a big problem. This is not an equation, right? So I have an equation for the first moment that depends on the second moment. So I cannot solve it. What would you do with this equation? What would you do once you find this situation? Why, great. Find an equation for the second moment. That's actually what I did. Well, it's not that. And then what you can do is, well, then I write an equation for the second moment. I multiply by n squared, my master equation. I do the algebra, and I get this. Well, let me keep this and then I cross it out in case you do the math yourself. You can compare. Minus 2. So far, good, no? I have the second moment, the first, the second. I have 2 variables. I can solve it, and then I have this. And cube. What do I do next? Do you want to have lunch today, or I give you the question? If you can do it, you can continue, but the equation of the moment k minus 1 is always coupled to the equation of the moment k. We have an infinite hierarchy of ordinary differential equations for the moment of the distribution. Why? Because I have this nonlinearity here. When my master equation was linear, the moments are independent, perfect. When my master equation is nonlinear, then things change a little bit. So what can I do? Well, the first thing that you can do is you can come here and you say, well, I have this. I do this. It's just moving a 2 up. Why? Great question. Why? Why? What does this approximation mean? This is an actual approximation. This is called mean field approximation. In all the books, I don't know why they call mean field. Well, they know why, but it's not related to mean field in Ising model and things like that. It's somehow, but what is behind this? Forget about the name. What is behind this approximation? What? The variance equal to 0. So what does this mean? Let me go here. The variance of n is equal to n squared in value minus. Actually, what I'm doing is I am assuming that this is much smaller than the mean value of n squared. And if you want to play with relative fluctuations, what I am assuming is that the variance of n divided by the mean value is much smaller than 1. So what I am assuming is that my distribution is very, very, very narrow relative to the mean. I'm assuming small fluctuations. When is this true in statistical mechanics, for example? Have you taken statistical mechanics courses? Large systems, large systems, when my system is large. And when my system is large, it's because, I mean, the mean is a well description of the system, no? I kill fluctuations. Okay, let's solve this equation with this as an approximation. This is my equation. The time derivative of this is equal to b minus delta, beta minus delta n minus gamma L square n square. This, you can even solve it exactly, the ordinary differential equation. As we've been doing so far, let's look at the stationary state. And what we would get is that the mean value of n in the stationary state is equal to beta minus delta divided by gamma L square. Or if I want to work in terms of densities, which is usually the case, this is beta minus delta divided by gamma, assuming, defining U as n divided by L square. Okay, so this is what we get under this approximation here. Many of you may be wondering, well, what does it mean? When is this approximation going to be correct, no? So let's try to, okay, the order maybe is not the best one, but okay. So what you see now in the screen, this is numerics, okay? So the way you obtain these distributions is basically by running this stochastic process for a very long time, and then you record the number of particles and you construct the distribution. Notice that this is density. 10 is, because of the parameters I chose, is beta minus delta divided by gamma, okay? And the only thing I'm doing is I have the same parameter values, but L square is different. L square in one case is 200, and in the other case is 36, for example. Who wants to tell me differences between these two distributions? And the color doesn't count. Yes? The peak is not the same. Okay. That was not the first one I was expecting, but is the one that we are more interested in. The variance is different, and the mean or the mode is, the mode, we don't know if it's the mean, the mode is shifted. Right? The purple one, we could say, well, maybe the mode is not in the black line because, well, that's a histogram and you just don't get it because don't have enough data. But in the orange one, is clearly not, the mode is clearly not in 10. No? Yes? This is the question I was waiting for. If you run this longer, would you get your distribution shifting towards the black line? Who says no? Well, you said no, but raise your hand if you think no, and raise your hand now if you think yes. Okay. This is our direct numerical simulation of my stochastic process. There are no approximations here so far. What is an approximation is this result. This result is telling me that the density in the stationary state does not depend on the system size. And in that case, I'm getting that it depends on the system size. But it does not depend on the system size when it is large enough. Let me show you another example. So what you see now as noisy trajectory in both panels is one single realization of this process. So I started with density 5, and I allowed it to run for time 50, and I just show you how it goes up and down all the time. The black line that you see in the screen is, again, the result that I get from neglecting fluctuations. And the dots that you see is the numerical mean value that I get by averaging over, I think it's 1 million of these realizations that you get there. So just to explain myself more clearly, the way I get the points is I run 1 million of these trajectories, and then I say at time 5, at time 0, how many do I have? Density always 5, because that's my initial condition. At time 10, I do the average over the 1 million realizations, and that's the number I have there, okay? That's why it's so smooth. So what do you see in both cases? And I tell you, this is 1 million trajectories. If I had done this 10 million, 100 million, it converged already. So it's not lack of data. It's an actual physical or mathematical result. It's not the same. What is not the same? It's lower than the black. In the purple, I would say it is as well, no? Yeah. So the purple and the yellow, or the orange, are both below the black, and the orange is lower. In the case of the orange, the difference is bigger than in the case of the purple. Okay. I have a question. Why is always lower? Yes, but why is not higher? Why the dots of the numerical average are not above the mean value? And how that prevents me from getting the dots above the black line? The variance? The variance cannot be negative. Great, that was the answer I was looking for. The variance is positive, right? That means that the mean value of n squared is always greater than the mean value of n to the power of 2. So I am replacing something by a number that is smaller, and therefore what I have here, it's always, wait a second. I'm very bad doing these arguments of what is bigger than this, but the idea is that this number is bigger than what I am having, which means that when I plug it here, my approximation always tends to overestimate the population size. That's why the black, which is my approximation, is above the real one. Great. But when I ask you how would you improve this first moment approximation that was coupled to the second, we got this very smart suggestion that I cannot believe I erased. I did, okay. We got the very smart suggestion of saying, but we can write a dynamical a differential equation for the mean value of n squared. And we got a bunch of terms, and at the end we got something that was proportional to the third moment of my distribution. And then we said, well, I cheated a little bit because I told you, well, since the second is coupled to the third, let's cut in the first, right? A question that you may have is, why don't you cut in the second, right? The more moments you have, the higher order is your approximation, I would expect the better it will be, right? So the fact that the second moment is coupled to the third, of course, doesn't mean that I need to go back to my first approximation. What I can do is I can choose a different, and this is what are called moment closure approximations, because it's a way of closing the system of coupled differential equations. And there are many of them. People try to understand what are the ones that work better in different scenarios. It's, I I mean, in the 80s, it was very famous. I mean, it was a very active field of research, especially for when you have spatial moments and things a little bit more complicated. But I can say, well, if my n is a Gaussian, follows a Gaussian distribution, or follows a normal distribution, then the third moment depends on the second and the first, because that's a property of normal distributions. And I can say, well, because I did my numerics first, that's more or less a normal distribution. Let's see how it works. At least it doesn't have huge skewness, or doesn't have. So then the approximation that I can write is replace the third moment by this linear combination of first and second moment. Well, not linear combination, sorry. This combination of first and second moments. And this is called the Gaussian approximation. So if you want to play around with this approximation, the only thing you have to do is to plug this here. And by doing this, you are incorporating information about what in your approximation? The second moment? What was that the second moment was representing? We discussed it in the beginning of the class. Fluctuations. I'm incorporating information about the fluctuations. And then what you have is a two-dimensional dynamical system. Let me clean this. I have a differential equation for the first moment. I have a differential equation for the second moment. How many of you have taken nonlinear dynamics courses? I guess not many of you. Okay, but I can basically do the same I did with one single differential equation, but with two. I find the fixed points that now, of course, are going to be a pair for the mean value and the second moment. Now you will need to check for stability, and I don't want to confuse those of you that haven't taken courses on dynamical systems, but it's very simple and it's fun. I mean, if you are able to do things that you are already learning, this is not gonna bother you too much. And then with the solutions that you get from here, what I'm going to show you now, it's only NST, because we are discussing the mean. But of course, you also have the second moment. You can look at the variance, for example, and you can compare the variance that you get from this approximation with the variance in your numerical simulations. Okay? So this is the next step we have. What you see now in the screen, and I hope the colors were a good choice, is the same we had before, but now the red line is the solution that I get for the mean number of particles out from this two-dimensional dynamical system in which I am feeding the information about the fluctuations. Right? And you see that, of course, now the agreement is much, much better. For this case, I would say it's almost perfect. It matches the simulations. Why? Because I'm accounting for the source of disagreement between the simulations and the first approximation. Okay? But this is very important. An exercise I used to have the students in my course here make was to do simulations of this process and compare it with the black line. And then many of them were struggling with 3 weeks with their code, trying to understand why the dots were not matching the black, trying to look for bugs in your code. There is no bugs in your code. And this is very important, because if you start learning about this topic more and more, in many, many cases, they will give you this solution as granted, and it is only valid, that solution is only valid when fluctuations are so large that you can delete, sorry, when the system is that large, that fluctuations are small and you can neglect them. So who can tell me now, if I ask you to do an exercise about thinking a little bit about biological processes, who can tell me why, if I work in, I told you, no, I work in ecology, why I am so interested with small systems? Small populations. What happens when any, see, so if this, imagine that this X here, this N, is a very, very pretty, I don't know, bird that we have in Tenerife. Why, for me, the N small case can be interesting? Because it's linear. I'm thinking about the ecologist. Ecologists probably, well, they know what is linear and non-linear, but no, in real life, Because
populations in real life are not huge.
Well, populations in real life are not huge sometimes. Yes, when the system is very small, I have complicated things that may go on.
You can model population and extinction, for example.
Exactly. So if I want to quantify the risk of losing my pretty bird, then fluctuations are going to be really important. And that's what we are going to do tomorrow. Tomorrow we are going to go back a little bit to introduce Fokker-Planck equations and Langevin equations, stochastic differential equations from the recipe, from the roadmap we constructed the first day. And we are going to try to understand the structure of those equations and how much information can we obtain with them, and how can we quantify things like, for example, extinction. Extinction is important if you are interested in ecology. If you are interested in getting rich, you may also be modeling this as the price of some stock market or stock price, and then extinction might be the time at which your stock reaches the price at which you want to sell to maximize. I don't know. I don't know the jargon there, but in finances, there is a lot of stochastic models, of course, and trying to understand the probability that my price will reach this value, will reach the other, blah, 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 blah. So on and so forth, okay? But that's what we are going to do tomorrow. So today I think I don't have more plots to show you, and tomorrow I won't have more plots. So yeah, questions? Any question? Yes?
I don't understand how to compute the second momentum in the stationary state.
I'm not going to write you the actual equations, but in mind that your equations are x and y. And you have here fxy. And here you have gxy. If you want to obtain the second moment, basically what you have to do is you have to solve this system of two algebraic equations. And this may have a solution that is x star and y star. And on N3, no, because I did this approximation. No. I need to plug this to break that dependence. Otherwise, yes, you are right. Otherwise, I cannot. Yes? Yes? Yes, tomorrow I will show you why. Yes, you will need to live without that until tomorrow. But tomorrow, yeah, we will see why. Yeah, and it's a very, very nice result. But yeah, tomorrow. Yes. Yes. Yeah, so system size in the context of the population that I put here for you is the area in which my animals can live. If you think about a physical system, let's say I want to look at chemical reactions in this jar, the system size will be the jar. No? So, and the idea is that the reactions between the molecules are going to be more frequent if my jar is smaller, because if I have 10,000 molecules and my jar has So the rates have to scale with density. We will see that tomorrow. Yeah, more questions. Questions, comments, complaints? Yes.
At the level of making computations,
Yes.
would it be useful to, okay, so I obtain n the first momentum. I could plug them again in that equation and repeat the process in an iterative way, so I improve precision.
In which equations? In the uncoupled equations or?
Third momentum equation.
But so this is not a differential equation. This is a relationship. Okay. There is a way of testing for validity of the approximations that we will see tomorrow. It's related to his question. Yes. This one? So this is, if I assume that my random variable follows a Gaussian distribution, this is the relationship that connects you the third moment of a Gaussian distribution with the first and the second. The approximation is to assume that n is Gaussian. If I give you a Gaussian, if I tell you, go to your computer and generate for me 3 million numbers that follow this Gaussian distribution, and you compute the third moment, the second, and the first of that series of numbers, or even more, if we get actual physicists, if I give you, this is the normal distribution, I give you the PDF, and I tell you, solve the integrals that give me the expression between the first, the second, and the third moment is this. This is an exact result. What is an approximation is to assume that n is Gaussian. So the thing is, in the Gaussian distribution, once I assume Gaussian distribution, this is already, I can do it. What I can do is I can look for better approximations, better moment closure approximations. So there is, especially in the spatial systems, when you need to approximate the spatial correlations by assuming independence of the particles and things like that, sometimes people, what they do is they try 4 or 5 that are available, and and it's something people are still trying to understand. So there are more moment closure approximations that work better in different scenarios. The nice thing is that if you assume Gaussians, then this result is exact. What is an assumption is that your variable is Gaussian. Yes? We have here a very, very, very good question. Is it valid to assume that my population is Gaussian if the distribution is small? What do you think? Let's do, well, first of all, if my population is small, remember that n is a discrete variable. So if my population is small, we saw the first day that things deviated a little bit, but it was not that bad, no? But there is a very, very, very important thing about the problem, at least that we are treating here. This is a problem that we are treating here that will make this Gaussian approximation a little bit bad for small populations, which is someone, well, my n, my variable, is defined only for positive values, right? So if your population is small, and that's something we're going to calculate tomorrow, and that's something we are going to discuss tomorrow, this model that I'm introducing to you, sorry, I'm giving it back to some of you, has something that we call an absorbing state. What is an absorbing state? An absorbing state is an state that once my system reaches it, it cannot leave. What is that absorbing state? 0. So once n is equal to 0, both the mean value and the fluctuations are 0, because if I don't have particles, they cannot reproduce. If I don't have particles, they cannot die. And if I have no particles, they cannot collide. So in 0, my dynamics is frozen. And that is going to change the statistics close to 0. And that's something we're going to calculate tomorrow. What is the probability that my system reaches 0? How long it will take to reach 0? We are going to try to calculate those things. But yeah, Sorry, I give very long answers. Short answer, no. Not for this case. Yes. More questions? Yes?
So every time you increase the number of moments that you use, is that all you need, or do you need more relations between the moments? For example, in this case, do you need a relation between the second and first moment, or is that all you need?
A second and the first moment? No, the second and the first moment I don't need because I have explicit equations for them. So all I need to do is when I reach to the highest order equation, in this case the order 2, or the second moment, I need to rewrite the term that is going to couple this equation to the next one in terms of the ones that I want to describe explicitly, to decouple the system, basically. Yeah? No worries. More questions? Yes? The system size is related to N or L? L square. System size is L square. N is the number of particles, and what you have in the y-axis is N divided by L, which is U. Yeah, system size is L square. Yeah. But if my density, no, but that's a very important question because I was assuming something that is not that trivial. If my density is 10, regardless of the system size, of course, my simulations in the orange and in the purple one have different N, right? And this is because you can see it here. N is proportional to L squared. So in both plots, N is also changing. I rescale by L squared, so it's density and it's intensive. So it does not depend on system size. But just quickly, in the purple line, you would have 10 times 200, 2,000 particles, and in the second one, 10 times 36, 360 particles. Okay? Yes? We have a great question here. Is there a reason why it takes the same time to reach the stationary state? Yes, there is. You should know. Yes, sorry. This is, I was very bad in the experimental physics courses because of these things. Yeah. Now, it takes, well, now we don't know either because I hide the previous one, but I trust your memory. Yeah. Why is the same time? That's a very good question. Because the parameters, but the system size is different. So the system size is not affecting the. So when my population is small, when n is small, the term that dominates the dynamics is the linear one, right? It's the exponential phase. And this, well, here this term is negligible, so you will not see it in any way there. So what controls the initial phase before saturation is the linear regime of this equation. If you linearize this equation, you will see that it does not depend on system size. It only depends on beta minus delta. Yes. Yes. If you don't erase this term, the thing is that this term is so small that you won't appreciate the difference. Unless you have like tiny systems, and then probably what you will see is that they go to 0 all the time. So it's really hard to see any effect. More questions? No? Yes? Yes?
Yes. And we cannot neglect that term.
Yes?
Would we see a shift upward in the density? Because of
Yeah, that's a great question. In principle, you should, but it's really hard to see it because a lot of realizations are going to die. But in principle, you could, yeah. But it's a little tricky. Yeah. Yes? 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 Yep. Yes? Yes. Yeah, so the question here is what happens if you initially have a lot of them? Well, you would have exponential relaxation to the stationary state, basically because the only thing that you would do is that this term will change sign, and therefore the linear regime, instead of being a growing exponential, is a decaying exponential. Sorry, I was very fast, but of course, to get that, beta is greater than delta. So I initially, yeah. Why? What controls transients is always the linear term, and the linear term only depends on the ratio between beta and the difference between beta and delta. Sorry again? The question here is if we change the value of the mean population density, are we going to have the same result? We are going to see the same difference as long as you manipulate system size the same way. What is creating the difference here is L squared. Of course, if you go to huge numbers of n, then the difference that you need to introduce in L are larger, no, to get the difference. So basically, you need to, let's say, if you set these parameters in a way that for a system 200 and a system 36, your number of particles is massive, then to see small system effects, you need to go to system size 5 or 4 to get, but the trend, the behavior is the same. When do you find it? At which value of L depends on the parameterization. Yes. Yes. Yeah. So the question is if my particles are not uniformly or homogeneously distributed in a space, how this thing change? That was the PhD thesis of the first PhD student I advised. I can tell you what happens. What you get here is that this term, instead of being n squared, is n times the spatial correlation function of your population. How that correlation function emerges, it depends on the spatial dynamics, the way the animals move. Yeah. But you can either ask him, he's in the first floor. He will be super happy and explain better than me. Or you can read the paper. Yes. So the question is if for small populations, would it be too difficult to introduce male and female? In principle, introducing male, female, juveniles, adults, ancient people, young people, does not depend on population size. You just need to go here and formulate your model differently. Then, of course, the more variables you introduce, the more complex your math is going to be, of course. Yes. Sorry, the question was if introducing two species, for example, or introducing adults and young people, or young rabbits, would make the small population size limit more difficult. If introducing that in the small population size would be more difficult. My answer is that introducing that is not more difficult in one population size or the other. It depends already in the way you formulate your master equation, as we discussed before. You basically need to formulate your master equation as an n-dimensional master equation and then move forward from there. But something that is very important is that when you have two variables, then the fluctuations are a mean value of n squared, mean value of m squared, mean value of n times m, and mean value, there are cross correlations that we are not going to enter, but you have a problem about that. So I thought that the class was until 1 and then questions until 1:15, but it was the other way around. So if you have more questions, we can keep talking, but I don't want Gaston to kill me, so better we finish here and we have lunch.